Okay, good morning. So this is our final week where we're going to discuss some new material. We have class next week as well, but we're going to be spending those two classes on review for the final. So this week I would like to keep working on these formal power series, a specific type of functional sequence. Turns out to be very foundational. Then we're going to discuss analytic functions, and then we're going to look at this Taylor approximation. Now, there are two ways of doing this. Ultimately, you would like to think of something like this, a formal power series of A sub n, where A bullet is a sequence of real numbers, and times x minus x star to the power n. You should think of this as, in a sense, an object that collects all differential information of some function at x star. Now, formally speaking, this power series is like this. So it starts at a0, and then a1 times x minus x star, and then a2, x minus x star squared, and so on. When we had a differentiable function f, we didn't have necessarily this whole power series, but we had it up to first order, and we had higher order terms. So somehow, if however many higher order derivatives you have more terms of this. And then ultimately, if your function is very nice, then you have this power series. And for these very nice functions, this power series itself is a convergence series and so on. So we're going to get to that. Yeah, so there are two ways of doing this. Either you say, oh, we start with the Taylor approximation for CK functions, k times continuous differentiable functions, and then in the best possible case, we have these nice series. Or you can start with these series and say, in the best possible situation, you have power series that converges, blah, blah, blah. And if you don't have infinitely many derivatives, you can still do this, but only up to finite order. So we're going to do it the second way, because that's how they do it in the textbook. So we're going to look at the best possible situation first, and then connect it back to functions with finitely many derivatives only. So here are some examples. If I were to choose n for any n, a sub n to be 1, and x bullet to be 0, then certainly this becomes this series. We had seen this before. This is the geometric series, right? And it converges, in fact, absolutely, insofar as x is less than 1 in absolute value. I would like to say something more about this. And then here's another standard example. If I were to choose a sub n to be 1 over n factorial, and x star to be 0, then this becomes this. And again, this converges, if you want, by way of the ratio test or whatever test you want. So we had done this example explicitly. We said that this is equal to the function 1 divided by 1 minus x if x is less than 1 in absolute value. Now, I would like to say something similar to this situation for an arbitrary power series. Okay? Somehow, I would like to come up with an analog of the number 1 for a more general power series that allows me to say, oh, if the input value x, or perhaps x minus x star, so the distance of x to x star, the center point, is less than this value, then the power series converges. It turns out that there's a theorem like this, and it is called the Cauchy-Hadamard or Hadamard theorem, and that uses the notion of the radius of convergence. So this is an important definition. Even though, of course, our functions here we're taking x to be real value, x to be a real number, more generally speaking, power series can be considered on a complex on the complex domain or even on more general spaces. And that's why people call it the radius, because they want to think of sort of the ball on which the series converges. So the radius of convergence of the formal power series is, by definition, the following. I'm going to call it rad of A bullet, because somehow it only depends on the sequence of coefficients. And this is defined like this. Essentially, this is supposed to be the reciprocal of limsup of the root sequence of an. In a second, we're going to see why. And so if you want, we can write it like this. So this radius of convergence is infinity if the limsup as n goes to infinity of the root sequence is 0. So infinity is supposed to be 1 over 0 if you want. The reciprocal of this, if this is a finite and positive number. Let me start recording. Yeah. Say in 0 to infinity, endpoints not included, and it's going to be 0 if limsup is infinity. Again, 1 over infinity would be 0 in a sense. So 0 Okay, so now with that, so for instance, we can say that the radius of convergence of this guy is 1, right? Because a sub n is a constant sequence, which means that the root sequence is also constant, which means that the limsup is 1, which means that the radius of convergence, I should be looking at this case, is 1 over 1 is 1. And somehow you see this radius of convergence detects this number. What do you think? Do you have any guesses as to what the radius of convergence of this is?
It looks like it should be infinite.
Right, because this is supposed to be exponential function, and like there are no sort of like fine print there. For any x, this should make sense. And indeed, I'm going to leave it to you to verify that the radius of convergence is infinity. Okay. In other words, the limsup of this sequence of 1 over n factorial is 0, which does make sense because n factorial grows faster than any exponential. And we said how this root sequence basically compares whatever sequence you have to exponentials. And so because this guy decays faster than any exponential, its limsup has to be 0. Okay, that's a very nice exercise. I highly recommend this. So. Okay, and so now I can state the Cauchy-Hadamard or Cauchy-Hadamart Theorem. For French names, you're not supposed to say the first H. I guess also you also don't say the last D. It says the following. It quantifies or it tells you when this power series converges uniformly, absolutely, whatever, or when it diverges. And it will be based on the root test, the proof, and the statement, really. And it says the following. Cauchy-Hadamard, I think, proved this as part of his PhD thesis. But you see, 150 years later, it becomes like an undergraduate thing. So let this be a formal power series. Formal power series. Then I'm going to have three statements. First, yes. How do I want to state it? Hang on. OK. I'm going to state it like this. The series converges absolutely and pointwise. So absolute convergence is that this converges with absolute values added. And remember, absolute implies regular convergence. Absolutely and pointwise for x in the open interval centered at x star with radius rad. Or if you want, open ball. So if your input value x is less than rad close to x star, then you have convergence. But it is pointwise, OK? If you give away some radius, n epsilon from this, then you get to have uniform convergence as well. Namely, so more specifically, for any r that is strictly less than the radius of convergence, this series is convergent, converges absolutely and uniformly. And uniformly on, so for x in the closed interval, closed ball centered at x star with radius r. And finally, if your x is more than radius of convergence away from x star, then the series diverges. Absolute value. Okay. Now, note that if I were to plug in x equals x star, then all of these terms would be 0. So this obviously converges. So that's not the point. The point is that if you can get convergence for x nearby x star, because we want some sort of infinitesimal information, just like we did for derivatives, if you want. Okay. Another thing is that I've been thinking why this is sort of like a different thing, in a sense, formal power series, or formal series in general. Because in a sense, this is a bizarre thing to do. It's like before even considering whether, or before even verifying that this thing makes sense, we're already using some symbol to denote it. Because if you were to think about it, this is just saying, if you're just looking at an infinite formal series, when you write this expression, you really mean the limit of the sequence of partial sums. So we're using a symbol to denote the limit, even though the limit doesn't necessarily exist. So it is kind of surprising, I think. Okay, any questions about this? About this statement? Okay, and so the proof of this is based on a certain limit law for limsup, which I'm going to leave as an exercise. At this point, I think it's not very surprising that limit laws, there are limit laws for limsup and stuff like that. They're not as nice as limit laws for limits, but still, they are good enough. And the limit law that I'm going to give as an exercise has to do with the limsup of the product of two sequences. Okay. This is, again, a very nice exercise that I'm going to leave to you. This guy is less than or equal to the product of limsups. That's supposed to be an absolute value. And in fact, we have equality if at least one of these sequences converge. And there's a similar statement for lim_inf, but we're not going to use that. I think you need to change the order. But in any event, once I have this, here's the proof. So you see, I'm going to try to apply the root test to this series itself. Okay, so I'm going to have to take the 1/nth root of this term, or rather this term in absolute value. So let's start with the proof of 1. So I'm looking at this guy, taking the absolute value, and then raising it to the power 1/n. Of course, this distributes, and this just gives me this. Okay. Now, in fact, in this case, one of the sequences, one of the sequences here is this sequence, and the other sequence is, let's say, this constant sequence. The limsup of this is the limsup of this times this. Okay, let me just write it like this. Lim upper bar, remember, was sort of an abbreviation for limsup. And this is this. Now, if x is at most radius of convergence close, or far from x star, then that means that this is bounded by rad of a bullet. And rad of a bullet is precisely the reciprocal of this number, extended number. In any event, when you were to multiply, if you were to multiply both of these, you're going to get some number that is less than 1, strictly less than 1. Which means that by the root test, this guy has to converge absolutely. Test, we're done. Because the root test was all about looking at the limsup of the root sequence of this guy. And it said that if this limsup of the root sequence of the terms that you're adding is less than 1, then you have absolute convergence. If it's greater than 1, then you don't have absolute convergence. You have divergence. Okay? That's how we do it. Any questions about this first part? The second part is not quite the same thing as the first part because, so you see, the root test only tells us pointwise convergence. It really works only for series of numbers, but if I were to fix an x value, now I have a series of numbers. But now if I want to sort of like upgrade it to uniform convergence, I need to do something. Do you guys remember something that I can use in this context? What can I use to deduce the uniform convergence of a series of functions? There's one tool, basically. There's a test.
The Weierstrass M-test.
Exactly. So M-test, we're going to have to use the M-test here. So the M-test says the following. Remember? It says that if you have a functional series, and if the numerical series consisting of the C0 norms of the terms that are the functions, then the functional series converges uniformly. That's what it says. Maybe I should remind you here, because this is important. And in the problem set that you're probably working on now, there are problems about this. So, recall. M-test. If this guy converges, so this is a series, numerical series of C0 norms, then the series of functions, functional series, converges uniformly and absolutely. So I want to use this. So that means that I need to handle the C0 norm of these functions. Right? So now f sub n is this function. Let me write it. F sub n of x is this nice polynomial function, after all. Right? So if I were to take the absolute value, I would get this. You see, I've taken some r that is strictly less than the radius of convergence. Well, if I look at this, the sup of this, it's in fact the max, right? The max is exactly what? What is the max of this where x varies in this interval? Polynomials are continuous functions. They attain their maximum on closed and bounded intervals, and this certainly is a closed and bounded interval. Assuming, oh yeah, okay, it is a closed and bounded interval. So what is the max of this function? N is fixed. I'm varying x as x. So I'm varying x in this interval.
When x minus x star equals the radius.
Right, because this takes the value 0 at x star. And depending on the exponent here, either it's going to be sort of an odd function or an even function. But in any event, it's going to look like this. Right? And if I were to take the absolute value, it always looks like this, basically. And it takes the max when this distance is exactly r, capital R, over here. This one. And so if I define it like this, then its C0 norm on this interval is a sub n in absolute value times r to the n. But again, by so on x star minus r, x star plus r. Of course, if I were to change r, this norm would change also. But then again, by the same reasoning, the limsup of this is the limsup of this times r, but r is strictly less than the radius of convergence, which means that the limsup of this is strictly less than 1. Again, then, by the root test, I can deduce that the C0 norms, or rather the series consisting of the C0 norms, converges. Then I can apply the M test to get uniform convergence there. Okay. By the M test, we're done. And finally, the third part I'm going to leave to you, because if this is greater than the radius, again, you're going to look at sort of the product, and you're going to see that there is no way for this to converge by the root test if you want. So this is an exercise. Any questions about this? Okay, so here's an example. Let's look at the geometric series. So now I'm adding the terms x to the n. So a sub n is 1 for any n, and x star is 0. So I have the geometric series, and for x in absolute value less than 1, this converges, and so on. So right? So limsup of this is 1. So the radius of convergence is 1, the Cauchy-Hadamard test theorem would predict that for x in absolute value less than r, you have pointwise convergence. So when I write this equality pointwise, because by definition this is supposed to be a limit, I'm saying that this sequence of functions of partial sums converge pointwise to this function. I'm going to say a couple more words about this. And then for any x less than 1 minus epsilon, for sufficiently small epsilon, for instance, then this convergence is uniform. Now, what was the distinction between pointwise convergence and uniform convergence? Do you guys remember? Like, if we didn't know the Cauchy-Hadamart theorem, how could you sort of justify that indeed here this convergence is pointwise, but up to an epsilon, if I were to get rid of an epsilon, then my convergence becomes uniform. So you see, I can upgrade the notion of convergence, but it has a cost, some epsilon. What is the difference between pointwise and uniform convergence? Or is this something surprising, perhaps? What is a heuristic that I can use to sort of make sense of this, even if I didn't know the theorem or its proof?
It's been a long time, but I remember something about functions staying within like an epsilon ribbon that shrinks down. And uniform convergence keeps a lot of properties that we like continuity and differentiability.
Yes, but in this case, differentiability and continuity is not a problem, you see. Because for any epsilon, this works uniformly. Somehow, something happens as x gets closer and closer to 1. What happens when x equals 1? There's a blow up, okay? This guy blows up at x equals 1. Now, I highly recommend sort of putting these on Desmos. Do sort of like a finite sum. On Desmos, you can do this. You can put like k equals 0 to n, where n is a variable that is an integer, and sort of make Desmos plot this and sort of take n to a sufficiently large number, and you're going to see this convergence actually. Now you see, the Cauchy-Hadamart theorem doesn't say anything about what happens when the distance between x and x star is exactly the radius of convergence. Because then you're at the boundary. The product, the limsup of the product becomes exactly 1. And I told you, when things are equal to 1, sometimes it becomes complicated. And there are other tests that allow you to sort of handle, in certain situations, these blow-ups, but we're not going to get to that. So here's a picture, okay? I have an asymptote here at 1. And here's minus 1. And if I were to plot this, let me call this S infinity of x. Okay. And S sub n is the partial sum up to order n. Okay? And so when I'm writing, for instance, here, this formal series is equal to this function pointwise, I really mean that this sequence of functions converges pointwise to this function. And otherwise, if I were to write here, because I'm writing uniformly, I mean this sequence of functions converge uniformly to this. Okay? On a different domain, though. So what's happening here? So this guy, right, so S infinity, takes the value 1 when x equals 0. And when x equals minus 1, it takes the value 1/2. So it's somewhere like this. But of course, as I'm increasing x to 1, there's an asymptote. There's a vertical asymptote. So it's like this. That's my S infinity. How about the partial sums? Well, we had computed this. In this case, in fact, we can come up with an explicit formula for this. And there's a trick involved. Namely, you do the following. So I'm doing this again because this is an important trick. And even though even I have trouble sort of remembering this, at the very least, you should be able to sort of derive it again. So you have this. So this is 1 plus x squared all the way up to x to the n. But then I can multiply this 1 minus, multiply it by 1 minus x. And then I have to divide by the same thing so that I have equality. Then opening the numerator, I have some cancellations. Okay, 1 plus x plus dot 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 plus x to the n coming from this minus x times x squared minus x to the n plus 1. Minus x squared minus dot 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 minus x to the n minus x to the n plus 1. Divided by 1 minus x. Let's cancel. Then in the numerator, you're left with 1 minus x to the n plus 1 divided by 1 minus x. Okay. Now you see, okay, let me ask you this. This now, instead of writing this partial sum, I could have written it in that form as well. It's the same function. What is the fate of this function if x is equal to 1? Certainly it is not defined, but at the very least I can think of the limit. Right? What is the limit of this as x goes to 1? I cannot plug it in, of course, because it's not defined there. But at the very least, I can look at the limit.
It'd just be 0.
Right? How do you do that?
Well, if you just plug in like infinity per se for x and see.
Why not 1?
Oh, 1. Yeah.
Yes. I'm asking what this guy is doing when x equals 1. Yeah.
Right. So when x equals 1, you have 1 over 1 minus 1.
Well, shouldn't it be 1 minus 0 divided by 1 minus 0? Sorry, 1 minus 1 divided by 1 minus 1, which is 0 divided by 0. So how do you handle that? You can use L'Hopital, right? Which says that the limit of something exists, or rather, if the derivative of the numerator exists in the limit, and, let me say it this way. If the limit of the derivative of the numerator exists, and likewise for the denominator, then the limit of this ratio is the limit of the ratio of the derivatives. In other words, so let's do this. Limit as x goes to 1 of s sub n of x is limit as x goes to 1 of 1 minus x to the n plus 1 divided by 1 minus x. So this is an, it's indefinite, right? It's 0 by 0. And then you differentiate these. The denominator becomes minus 1. And then the numerator becomes minus n plus 1 times x to the n. And L'Hopital says that whenever the limit of this exists and the limit of this exists, this limit of the ratios is the same thing as the thing that you're trying to compute. In this case, then you can plug in. Okay? Did I make a mistake somewhere? Well, I guess in this case, we can just plug it in here, right? Instead of taking the limit here. So if I were to plug in x equals 1, because it should hold there anyway, I'm just adding 1 n plus 1 times. L'Hopital still works, of course, but it just gives me n plus 1. In any event, it's a finite number, you see. S sub infinity is infinity at 1. On the other hand, S sub n is a finite number. And maybe let's compute, for instance, what happens when x equals 0. If x is 0, S sub n is going to be 0, of course. And I know that this is just a polynomial after all. So it's like this. So you see, as the input value x gets closer and closer to 1, S sub infinity diverges more and more from S sub n. Maybe I should draw this better. So okay. So this is 0. This is 1. Let's say this is minus 1. This guy is S infinity. It has a vertical asymptote. So for instance, S sub 0 would just be the constant function 1. S sub 1 would be 1 plus x, and so on. But in any event, oh, I guess should be at 1 here. So this guy is S sub n. For uniform convergence, we were looking at an epsilon strip around the target function, vertical strip. Okay. And for uniform convergence, we needed that the graph, the complete graph of the approximating sequence, be inside the epsilon strip around the target. But you see, if you allow x to escape to 1, then there's no way for any of these red graphs, the approximating functions, to be completely inside this epsilon strip, because it just like blows up. But if I were to get rid of, if I were to block x from running to 1, if I chop it off here, now everything is nice. Okay. Does this make sense? Any questions? Comments? Okay, we have a couple minutes. So let's talk about derivatives then. And so ultimately, for instance, if my formal series converges uniformly, like your colleague suggested, we know at this point many of the sort of calculus properties are preserved. And so for instance, in this case, I have a very nice function in the limit. And for instance, I would like to say something about the derivative of this. I would like to be able to say that instead of differentiating this function, insofar as I can analyze it as a series that converges, I should be able to differentiate this series term by term to get the derivative of this. And likewise, I should be able to integrate these terms to get the integral of this. And that indeed happens to be the case. Okay? That's the next thing we need. And so for this, we're going to need, or maybe let me just give you some heuristic before going into the details. And this is also one of the benefits of doing things formally. I would like to be able to differentiate this series. Let's not worry about the convergence and whether or not this makes sense. But in the best possible situation, I should be able to change the order of these two limits, because this derivative involves a limit, and this sum too involves a limit. And we said how changing the orders of limits is an important thing that is applicable in some situations, and sometimes it doesn't work, right? But say we can do this. Then this becomes n times a sub n times x minus x to the star, x star to the n minus 1. The reason why is that n equals 0 gives me the constant term. So if I were to differentiate it, that should go away. So that's my indexing should start at 1. Okay? And a similar thing should hold, at least formally, when I'm trying to integrate. And tomorrow we're going to discuss when we can do this for power series that converge. Okay, thank you. I'll see you tomorrow. Okay, let's start. Good morning. So we're going to keep working on power series today. I would like to talk about differentiation and integration of power series, and then we're going to switch over to sort of functional interpretation of these. Now, yesterday I had mentioned this. If I have a formal power series of this form, a sub n, remember a sub n is some sequence. At this point, I don't care about whether or not this guy converges. Formally, I'm just interpreting, I'm just thinking of this expression. A sub n is a sequence of numbers times x minus x star. X star is a fixed number again, and x is a variable. Okay? Now, if I were to fix a p, then I can really come up with the formal pth derivative of this expression and the formal pth antiderivative of this expression like this. And so here I'm using the factorial symbol in case you're not familiar with this. For instance, n factorial is just a faster way of writing the product of all integers from 1 to n. Okay, and how does one come up with something like this? These expressions, well, I did this when I was preparing the class. Basically, what I'm saying is this: under in nice circumstances, I should be able to differentiate this guy term by term. In other words, let's just look at the integral actually, because I did this, I mentioned this yesterday. So for instance, for p equals 1, the first formal antiderivative of this series would be something like this, for instance. Really, I'm looking at this expression, okay? Integral from x star to x of this series. So now my dummy variable has to be some other number, some other value, some other letter. So let me denote it by perhaps t. Oh, t minus x star to the power n dt. I'm saying, so that's my Hail Mary. I say, oh, you know, if I want to integrate this guy, I should be able to integrate the terms and then add them up. So I say, oh, formally, this is true. In the formal world, you're allowed to do these kind of things. And so you put this integration inside, and now this becomes this. Okay? But now I can integrate this rather easily because I know how to integrate polynomials. A sub n. Now what is the integral of this? This should be t minus t star to the power n plus 1 divided by n plus 1. And I should be evaluating this integral at the endpoints. So let's write it out explicitly. T minus t star raised to the power n plus 1. Now I need to divide by n plus 1 so that I get back this if I were to differentiate. And then I'm going to evaluate from x star to x. This is x star, of course. So if I were to plug in t equals x, I get back x minus x star to the power n plus 1 divided by n plus 1. And then if I were to plug in t equals x star, this is going to become 0. That's why one of the endpoints I'm choosing as x star. Okay, and then, so now I have this n plus 1 over here. Okay, that's how you do it. Is this correct? I think it is correct. Right, exactly. Because, so, it's nice. So, for the first antiderivative or for the first derivative, perhaps these sort of expressions are somewhat of an overkill. But if you try to iterate this idea, which you should be able to do ultimately, then you want to sort of like make this more sort of automatic in a sense. And so how can I write 1 over n plus 1? I can write it as 1 over n plus 1 factorial times n factorial, right? So n factorial divided by n plus 1 factorial. So this is the product of all integers all the way up to n. This is the product of all integers all the way up to n plus 1, which means that this ratio is this. If I had the second derivative, I would have 1 over, for instance, n plus 1 times n plus 2. And then if I had 75 antiderivatives, then I would need to multiply n plus 1, n plus 2, all the way up to n plus 75. Okay? So somehow, when you're sort of like dealing with many derivatives, which in the final problems that you will be, this becomes more convenient. And in fact, there's an even sort of shorter way of writing this. This is what is called, there's like a, what is it called? It's called falling factorial or something like that. People also denote this by some other symbol, but it's not very common, so I decided not to introduce that. Now, here's an interesting or important exercise. It's rather pedantic, actually, but still. The radius of convergence of each of these series is the same. In other words, now, the perhaps thing that sort of unifies derivatives and antiderivatives here is that you see I have always n factorial in the numerator. This is my adjustment constant. And the denominator, I'm either subtracting or adding some integer. In the derivative case, I'm subtracting. In the antiderivative case, I'm adding. And then I'm adjusting the exponent as well. And you see, the integer in the denominator I see is also the integer that I see in the exponent. Of course, these vary as n goes to infinity. And in the derivative case, because, for instance, n equals 0 gives me the constant term. If I were to differentiate it once, the constant term would need to vanish. That's why you start, for instance, at n equals 1, n equals 2 or something. But in any event, I can sort of combine these two cases and say the following. For any integer, p, limsup as n goes to infinity of the root of this, but I should be taking the n plus p roots of this expression. So n factorial divided by n plus p factorial times a sub n in absolute value raised to the power 1 divided by n plus p. So this is the, for instance, radius of convergence, both for this and this. If I were to pick p to be a negative integer, that would give me the derivative. In any event, this limsup is the same thing as the limsup of the root sequence associated to the original series. Of course, as an extended number. And then radius of convergence, remember, of a series was the reciprocal of this number, which means that whenever one of these converge, the other ones also have to converge. How to say? Any formal power series has the same radius of convergence with any of its formal derivatives and any of its formal antiderivatives as any of its antiderivatives. You see, this is very beneficial because initially, when you start with a formal power series, there is a question of convergence. Does it converge uniformly, blah, 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 and you need to look at the radius of convergence. But once you figure out for certain values you have convergence, then in fact you can start doing calculus. Okay? So you sort of invest initially, and then you get to use calculus however you want. Now here's a theorem that sort of contextualizes this. What I would like to do here is that just like we can think of the series x to the n as a formal power series, but at the same time, we can think of it as 1 over 1 minus x, at least for x in absolute value less than 1, so that I can think of the formal power series, or I can think of the function that I happen to be able to analyze. So it can go from here to there, here to there. Somehow, equality in math, as you see, we would like to imagine that it's a symmetric relation, but it's not quite, at least psychologically. And so I would like to shift the focus on the function that this defines, which happens conditionally, you see, as long as x is within the radius of convergence. And so here it is. Theorem. Let's let a sub n x minus x star to the raised to the power n be a form of power series. How did I write this? Let me define I, the interval, to be x star minus the radius of convergence, all the way up to x star plus the radius of convergence, which might be, of course, empty if the radius of convergence is 0, in which case the theorem doesn't say anything. Define so radius of convergence of the sequence was the reciprocal of the limsup, remember? In this case, the radius of convergence is 1, for instance. So this open interval, which might be the whole real line, which might be empty, but it's a set after all. And so now you see I'm shifting my focus. F to be the function defined on I, defined by this. Take x, send it to this. Now this is well defined, that's the point. We had discussed this. The Cauchy-Hadamart Theorem says that f is a well-defined function. Okay, this is not this theorem. We have discussed how this makes sense, at least on this interval. Then f is C infinity. If it is infinitely differentiable. Okay, this theorem has 4 parts. Okay. It has antiderivatives of any order. Third, for any positive p, the pth derivative, remember this was my notation for the pth derivative. If I didn't have the parentheses here, that would mean iteration, pth iteration of f, composition of f with itself. But if you put parentheses, that means the pth derivative. Well, this is given by the power series that we wrote before, which I have forgotten successfully. N factorial divided by n minus p factorial times a sub n times x minus x star raised to the power n minus p, pointwise and uniformly on any compact subinterval. So again, this is a limit, remember. I'm saying that this derivative, the derivative of this function, is this pointwise. So the limit of the partial sums converge to the derivative. And if I were to look at a compact subinterval of this I, then in fact the convergence is uniform in X. Pointwise, uniformly on any compact subinterval. subinterval of I. Remember, we had this issue with this as well. So for this is my function f. This is the power series. So I'm looking at I from -1 to 1. We saw yesterday, if I were to just look at this open interval, the convergence is pointwise but not uniform. But if I were to chop off the boundaries, and in fact any compact subinterval, then convergence becomes uniform. So my estimates become uniform. And the same thing with antiderivatives. For any p non-negative integer. So we don't have an established symbol for the pth antiderivative. So maybe let me just write it like this. Integral from x star to x raised to the power p. So you do this p times, okay? Of x, of f is this. From 0 to infinity n factorial divided by n plus p factorial a sub n times x minus x star raised to the power n plus p, again pointwise and uniformly on any compact subinterval. Okay. Things are getting complicated. I mean, this is the last week of new material, so as you see, everything is sort of like coming closer, getting together, and we're sort of seeing everything that we studied throughout the semester sort of come together in a nice fashion. And indeed, formal power series, or rather power series and functions that can be analyzed this way were very important for a very long time in math, and it's still important, of course. And a lot of sort of these tools that we've discussed throughout the semester was to make sense of statements like this. Okay. Now, I'm not going to give a detailed proof of this. Let me just mention that, of course, 1 follows from 3, because I'm saying that for any p, the pth derivative exists. That's literally what it means for f to be c infinity. For any p, the antiderivative exists, the pth antiderivative, which means f has antiderivatives of any order. The fact that this converges and this converges in these fashions follow from the exercise that I gave you. I told you that the radius of convergence of this and this are the same. And by the Cauchy-Hadamart theorem that we discussed yesterday, I have pointwise convergence and uniform convergence on any compact subinterval. Finally, the fact that what this converges to is the derivative, and what this converges to is the integral, follows from previous problem sets, where we had a sequence of functions converging to a limit, and we said, oh, the derivatives converge as well and stuff, or the integral converges. And so let me just summarize what I said. 3 implies 1. Four implies 2. The series, so this is the first item. The convergence of series follow from the exercise. That the series converge to the claimed limits follow from previous problem sets. To the pth derivative and antiderivative follow from previous problems. We could spend more time on this theorem, but I decided at this point, because I'm feeling you're sort of on the verge of burnout, I'd rather not prove this and instead give an example. And also, let's take a moment to appreciate how the nature of our proofs changed over time. Right? In week 1 or 2, I was being very careful about every single step. I was sort of giving you more details, writing things out explicitly. And 2 months later, 3 months later, now I'm just referring to other things that I allegedly did before. Okay, so this is how math works ultimately. And at the research level too, you don't sort of like prove things that are clear. Eventually, it's like you take classes, you read books, and you read papers, and humanity sort of metabolizes certain ideas. And at that point, people believe you when you say certain things. Okay. One of the designing principles for this class, when I was designing the class, was that I talked to a bunch of students who took this class before, and the general sentiment was that, oh, this class is pretty much like calculus, but with more steps, and there is nothing new. And I hope we were able to discuss some things, at least, that we can say, faithfully that, oh, this is not something that we could have handled in single variable calculus, and there is something different here going on, more advanced perhaps. It's not just like basic calculus with more steps. Any questions about this? Now, instead of starting from here, of course, so this machinery is useful when you start from the function itself. So here's an example. Let's think about log of x, so natural log of x. Let's say that I'm trying to analyze that function like this. Here's the proof. There are multiple ways of doing this, of course. Example. If possible. Okay. Now, let me also mention something here. This is like speculation on my part, but I think one of the reasons why this field this class is called analysis or foundations of analysis is this idea that analyzing a function has a certain meaning. It means to be able to write this function as an infinite series, at least for some x's. i.e., find a bullet and x star such that f of x equals this. At least for some x. Okay. And this is something that we do in math all the time as well. Somehow there are the names of the fields, algebra, analysis, topology, whatever. But also, within those fields, there are mathematical objects that are called those. So there's algebra as a field, but also algebra as a certain mathematical object. It's an algebra of matrices, for instance, or algebra of functions. Okay, so let's think about this. Perhaps, you can do this for different x star values, of course, but let's just find one. I think the nicest thing to look at is when x star is equal to 1. Because when x star is equal to 1, I know that f of x is equal to 0. So maybe I can sort of like come up with something. So let's do the following. I'm going to try to make f related somehow to pretty much the only series that I know converges, that I have a lot of control over, which is the geometric series. Okay, so how can I get something like 1 over 1 minus x out of log? And I get to differentiate and integrate too. So for instance, if I were to differentiate f, I get 1 over x. And then I can make this resemble the geometric series function by adding and subtracting 1 from this. Okay? So 1 divided by 1 minus x. Okay? But then this I can analyze. Now this is my independent variable if you want. So 1 minus x raised to the power n. Of course, now I need to bite the bullet. I need to restrict my x values. I'm saying, okay, so this works insofar as this value is less than 1 in absolute value. Okay? But the format I like is the other way around. It's not 1 minus x, it's x minus 1. So if I were to multiply this by minus 1, I could flip it. So this is this. Minus 1 to the power n times x minus 1 to the power n. Any questions so far? Okay. Now, this power series, based on the theorem, converges when x minus 1 is less than 1 in absolute value. And for x's that satisfy this, I can also take the antiderivative. But the point is that if I were to take the antiderivative of this, it's the same thing as f by the fundamental theorem of calculus. So let me be explicit here. So now 1 to x of this series, infinity minus 1. This is as close as you can get to actual magic working. Then you flip it. By the theorem, you get to do this. It's infinity. I mean, it's kind of like magic to me because I'm not used to functions that you can analyze like this. But okay, so this guy is also constant, so I can take it out. 1 to x. Then I know how to integrate this. Minus 1 raised to the power n times t minus 1 raised to the power n plus 1 divided by, x minus 1 divided by n plus 1. And so I have this. Okay. Now there's a problem with the indices. Even though this n starts at 0, I don't have the 0th order term here because the exponent starts at 1, as you see, which means that this expansion has a sub 0 equals 0. So a sub 0 is 0, a sub 1, right, to the first power. So n is equal to 0. So this is 1 divided by 1. So a sub 1 is 1. A sub 2 is when n is equal to 1. So this I have to divide by n. So that's a minus 1, plus 1/2, and then minus 1/3, and so on. Okay? So I was able to completely analyze log of x, and I was able to decompose it into a sum of polynomials. Okay? And of course, I don't need to go all the way to infinity. I can just cut it off at, let's say, n equals 4, perhaps. And from this, I have an approximation. And so what we just showed is that log of x can be analyzed like this for x minus 1 less than 1 in absolute value. Raised to the power n. Okay, and indeed, the radius of convergence of the series, I'm going to leave to you, is indeed 1. X star, remember, was 1 as well. That's what we chose. And so writing this out, it starts at 0. So the 0th order term is 0. And then when n equals 0 here, this becomes 1. Oh, it should be the other way around, I guess. Oh, yeah, so this is a plus, this is a minus, this is a plus. OK. When n equals 1, that's a minus divided by 2. Oh, hang on. I messed up the signs again. Huh. See this? No, that's correct. That is correct. OK. So now this is like this. X minus 1 minus x minus 1 squared divided by 2 plus x minus 1 cubed divided by 3 minus and then plus, minus, and so on, it goes on. But I know that the next term is going to be raised to the power 5, then 6, then 7, and so on. And I could, if I wanted, just concatenate everything and just write little o of x minus 1 raised to the power 5. So this is the 5th order or 4th order approximation, if you want. Okay. And if I wanted, I could have denoted this x minus 1 as h, so that it's similar, it's closer to the form that we know. Then x would be 1 plus h. So x is some value, some number that is very close to 1. And then this would give me that log of 1 plus h for h small is of the form h minus h squared divided by 2 plus h cubed divided by 3 minus h to the 4th divided by 4 little o of h to the 5. So far, all we knew was, I could differentiate this guy and look at the linear approximation. And before, what we had was only that log of 1 plus h equals, so log of 1 plus log prime of 1, right, the derivative, times h, plus higher order terms. That's what we had before. That was differentiability. Now you see, we have more control as to how this error term decays. And in fact, we can sort of like keep writing whatever our sort of resolution is. If you want more information, we could keep expanding this infinite power series, keep adding more and more terms with higher order powers, which would mean that for h small, they would decay even faster and faster, right? So if I wanted, I could get rid of those. But if I need to, I can be very explicit, very precise when I'm trying to approximate the function. Okay. And in a sense, many of the calculators compute the values or approximate the values of certain functions using expansions like this underneath the hood. Okay? Any questions about this? About 10 minutes. I'm going to do one more example. But before going into that, I want to say one more thing. Oh, by the way, I made DeepSeek compute this polynomial because this is, after all, a fourth order polynomial. And you can sort of open up all of these and then readjust everything to combine the coefficients and stuff. And it gives you some polynomial, but in a sense, this is more meaningful, this part. Okay. And if you put this on Desmos, you're going to see how the approximation works immediately. Now, tomorrow, what we're going to do is we're going to call this part, for instance, the fourth order Taylor polynomial of log at 1. So this part is going to be the fourth order Taylor polynomial. Not the Taylor who wrote the book, but Taylor who was a lot older, who passed away a long time ago. Brooke Taylor. Okay. Okay. So what I wanted to say is this: in this situation, log, I know very well. I could just handle logarithm, and I knew that its derivative is 1 over x and stuff like that. But even if I didn't know the function, even if it were sort of like more complicated, by just evaluating the function, I could have guessed this power series like this. We're going to spend more time on this tomorrow, but let me just say this. Assuming my function f, let's say I was given a function, assuming it has a power series expansion. Analyzed, so that I have f of x equals this series, at least for some x values, in a sense, if you know f to some extent, a sub n's too are determined by f together with x star. Because you see, this is, so a0, and then n from 1 to infinity. I just separated the 0th term. But then you see, this is an infinite series such that each of the sum n's have at least one factor of x minus x star. Okay? Times something, the remainder. The point is that if I were to plug in x equals x star, all the terms of this series is going to vanish except the 0th term. I'm plugging x equals x star. This part is going to vanish. I'm going to be left with a sub 0. And then if I differentiate this guy, let's say once, so that now I have n from 1 to infinity, n times a sub n, x minus x star raised to the power n minus 1. Again, to this, if I were to plug in x equals x star, all terms except the 0th order term is going to vanish. Okay, because n starts at 1, which means that the exponents start at 0. So 1, 2, 3, and so on, they're going to vanish, which means that f prime of x star has to be equal to 1 times a sub 1. Okay. And of course, I can take the second derivative. I can take as many derivatives as I want. Let's do one more. N from 2 to infinity, n times n minus 1. Hang on, is it like this? Yes, that's true. A sub n, x minus x star raised to the power n minus 2. And again, all but the 0th order term of this vanishes if I plug in x equals x star. Which means that the only term that's going to survive x equals x star is when n equals 2. In which case, I see that f double prime of x star equals n times 2 times 1 times a sub 2. So that a sub 2 really is f double prime evaluated at x star divided by 2 factorial. Okay, going on this way, going on this way, I have that if f can be analyzed this way, then it must be the case that a sub n is equal to the nth derivative of f evaluated at x star divided by n factorial. So okay. So for instance, that means that if I want to analyze, if I want to see if I can sort of analyze a function like this, I actually know, once I fix x star, what these coefficients must be. Now, whether or not, if I were to plug in those coefficients, this actually converges to this is a different matter, okay? And that is the difference between C infinity functions and real analytic functions. Infinitely differentiable doesn't mean that you can analyze the function. Okay. So warning. Not all functions, even if they were C infinity, infinitely differentiable, are analyzable this way. Can be analyzed. Analyzed. Now. Do you write this with a y or an I? Analyzed. Y? Oh, okay. Sorry. Yeah, this looked bizarre. Here to analyzed. This way. One example you already have encountered in the previous problem set. For instance, f of x is e to the minus 1 over x squared. You've shown that this function is c infinity, any of its derivative at 0 is 0. Okay? So the right-hand side, if you were to be able to write this as an infinite series, the right-hand side would just be the 0 function. But certainly this is not the 0 function. Okay? This is an important point. Okay, good. Tomorrow we're going to switch to Taylor approximation. Thank you. Okay, let's start. Good morning. So the course feedback for this class is open. You should have received an email. How many of you have received an email about this? Because sometimes students end up not receiving it. Please check your mailbox, and there should be sort of an email about this. This is not something that I'm conducting throughout this semester. For each problem set, there was one survey that I made you fill out, but this is university-wide, and please, write your criticisms and what you liked, what you didn't like, and stuff like that, so that we at the department know what works, what doesn't work, and how we can change it for the better. Okay, this is an important thing. Okay, so today we're going to define, finally, these functions that are analyzable in the sense that we discussed yesterday. And then we're going to switch over to finitely differentiable functions, and we're going to discuss this Taylor approximation theorem, which is very important. Probably we're not going to be able to finish the proof of it today, so that means that on Friday too we're going to be discussing it a little bit. And then on Friday, if there's time remaining, I would like to discuss a little bit this unicorn calculus, is what I like to say, operational calculus. Okay, so for this class, we go back to open intervals, I, lambda to rho. Now, so far we were just looking at expressions of this form, formal power series, and then we figured out when they are convergent, in which sense they are convergent, all that fine print. And yesterday we had started switching our perspective from the series to the function. So instead of saying, oh, I have the sequence of polynomials, and then I'm adding infinitely many of them, and then I want to be able to get a function at the end, now we want to start from the other side. We want to start from the function itself, and we would like to be able to say something like, oh, I can analyze a function. And here's the definition. If I have a function f, defined on my interval I, and if I fix a base point x star, I'm going to say that f is real analytic at x star if, well, there's a sequence a bullet and some radius r, such that f of x equals this power series, and this has to happen pointwise, insofar as x is within r of x star. Okay? I told you that this is sort of like all higher order derivatives of f at x star put together, which means that somehow, in a sense, if I were to change the base point, this expansion should change also, just like in the first derivatives, for instance. And of course, now we know that if this happens, then it must be the case that a sub n is the nth derivative of f evaluated at x star divided by n factorial. And in fact, I know what this r is too, at the very least, or I have a candidate. In this case, I'm writing, there is some a star, a bullet, but that a bullet, that sequence is fixed completely once you know x star and f. Nth derivative of f evaluated at my base point divided by n factorial. And of course, R should be the radius of convergence at the very least. It could be larger in principle. But let's say that R is 1 over limsup as n goes to infinity of the root of this expression. So I can just write it explicitly. The nth derivative of f evaluated at x star in absolute value divided by n factorial. All of these raised to the power 1 over n. And maybe I should say that this R is, of course, allowed to be infinity. I just want it to be a positive extended number, if you want. So this expansion must have some thickness. Certainly for x equals x star, everything on the right-hand side is 0, so there's nothing to do there. This doesn't give you anything. So I want some thickness. Oop. Okay. Okay, then how do I define real analytic function in general? Well, a function is real analytic if it is real analytic at any point. And let me denote by c to the omega. It's not c infinity, but it's a different space now. C to the omega to be the set of all real analytic functions on I. All real analytic. Functions on I. Okay. Now there's an important point here that's a subtlety. Real analytic, so the word real here, doesn't necessarily only refer to the fact that my function takes values in the reals, but in fact, analyticity, this is in the sense of real differentiability. Now, people really are perhaps more interested in functions defined on the complex domain or certain parts of the complex domain. And it turns out that differentiability in the complex sense is a lot stronger than differentiability in the real sense. And that sort of like really makes all the difference between complex analysis and real analysis. Okay? So in real analysis, throughout this class, we've seen so many different senses of differentiability, right? And so I would like to sort of summarize everything. And then I'm going to call this the Hölder hierarchy of functions. Of function spaces. So all of these functions that function spaces that I'm going to write are of the form regularity, open paren, the domain I, a semicolon, R, close paren. And so, but I'm not going to write this down because it just takes a lot of space. So initially we have the set of all functions, right? So this is how we started in week 1. I defined what a function is and so on. And then smaller than all functions is a set of all locally Riemann integrable functions. Within it, you have the set of continuous functions. Within C0, you have C1, and so on. And then you have C2, C3, and so on. And then you have CK, k times continuous differentiable. So you have k derivatives, and the kth derivative itself is continuous. Then I can keep going like this. And I reach the set of all infinitely differentiable functions. And even though I'm writing this like this, these are all strict inclusions. C omega, set of real analytic functions, is a proper subset. It's a smaller subset of all infinitely differentiable functions. But then I can keep going if I wanted. Because I can say, well, in a sense, polynomials are basically functions whose power series expansion just stop at some finite time. In other words, for a polynomial, a sub n would be 0 after finite n. And so I can say, eventually, I'm going to reach the set of all polynomials of degree, let's say, d at most. And then within this is the set of polynomials of degree d minus 1 and so on. And then I reach the polynomials of degree, let's say, 3. Within it is polynomials of degree 2. Within this is polynomials of degree 1. Within this is a set of polynomials of degree 0, which is nothing but the constant functions after all. You see, we had all these different sets of functions. And in a sense, analysis is all about looking at these different sets of functions and sort of understanding their properties, their limiting properties, and so on. And when you think about it too, this sort of hierarchy is, so you can sort of like map out your mathematical education looking at this set, this collection of sets. So probably you started with algebra. Algebra is just, in a sense, math with constant functions. And then they taught you things about lines, right? Y equals ax plus b and so on. And then maybe you learned things like the quadratic formula. So you switched over to this set. Okay? And then once you started learning calculus, really, most of the functions that you were dealing with were real analytic. Sines, cosines, exponentials, whatever. Then we switched over to this class. When we started here. We first defined the set of all functions. Then we went to C0, continuous functions. Then we talked about differentiable functions, finite order differentiable functions. So we looked at all this stuff. Once we were done with differential calculus, we moved to integrability. And you see, this is like all sort of coming together. And then, so you see, we did this, finite differentiability, infinite differentiability, integrability, so that we can talk about fundamental theorem of calculus. And then we talked about analytic functions. And of course, there is more, in fact. Between any two of these finite order differentiabilities, you have Hölder differentiabilities. Let me write that as well. This was sort of like in the context of differentiation in the weak sense. Because, for instance, you can look at once continuously differentiable functions, but maybe you can say more about the first derivative. Maybe you can say, oh, my first derivative is not only continuous, but in fact, it is Hölder of some exponent or something. And so for any k, we also had this. ck plus 1. And here I have ck. So this is included here, right? So because k plus 1 many differentiable functions are also k times differentiable functions, but not vice versa. But within this is the subset of k plus 1 continuously differentiable functions with the k plus first derivative bounded. My interval here is open, so that is not immediate. So you need to assume this. So with derivative bounded. So this is a certain subset. And we had done this with for k equals 0, but this holds in general. If you have the k plus first derivative that is continuous, also bounded, that means that this function, f, let's say, is in fact k times differentiable, and the kth derivative is Lipschitz. So this set is denoted by this. C to the k, comma 1. So now you're looking at the fractional derivative. You see, this is a notation that allows you to keep track of the differentiability in the strong sense as well as differentiability in the weak sense. But then, of course, if we had two exponents like this, theta 1, theta 2, any Lipschitz function, or rather any function whose kth derivative is Lipschitz, is inside k theta 2, k times differentiable with the kth derivative theta 2 Hölder. This is inside this. And then this is inside c k comma 0. C k comma 0 is the same thing as ck. So you have this hierarchy, and between any one of these finite order differentiability, you have infinitely many spaces as well. So you have these, like, all these knobs that you can deal with. For most pure math purposes, this stuff is not important, but when it comes to applications, when you're trying to solve differential equations and stuff like that, it becomes very important how regular your function is. Okay, because the more regular your function is, the more estimates you have, ultimately. Which means that if you're trying to approximate something with higher order things, you're going to be able to control the error margins much better. Okay? So that's that. Any questions about this? And this Hölder property, Lipschitz property, these things, it takes a while to sort of come to terms with their naturality. That's why I wanted to introduce them. And throughout this semester, we've seen these functions pop up so many times in problem sets and in class as well. Okay, so now I can talk about Taylor approximation. In a sense, we have done the Taylor approximation for degree 1. So up to first order, we already did it. Okay? This was in the context of the definition of differentiability, mean value theorem, whatever. The point of Taylor approximation is that it allows you to come up with higher order terms, ultimately. So, now I need to define something. It'll be the Taylor polynomial of a function. This is a very important definition. I'm taking an n non-negative integer, and let's say that f is Cn. So if n is 0, that means that f is continuous. If n is 1, that means that f is differentiable with the first derivative continuous, and so on. But I'm leaving it as a parameter, you see. And I'm going to take an x star, base point. In my interval I. Then, well, the Taylor polynomial of order n of f at x star is basically the partial sum of the alleged Taylor series of this infinite expansion up to power n, up to order n. Okay? So in general, at this point, I don't know if f has an infinite series that converges. I don't know if I can analyze f. But I'm saying, at the very least, I should be able to come up with the partial sums all the way up to n, because those require at most n derivatives. So I should be able to handle that. Then the order n Taylor polynomial of f at x star is the following function. So this is my notation. Now this is going to be a function. It's going to be a polynomial function, of course. Take an x and send it to this. Oh, that's okay. Okay. If I knew that my function f is real analytic, in fact, I could take n to infinity. But even if my function is not, so even if I have finite order differentiability, this makes perfect sense, you see. So let's write out a couple of these, because keeping track of this parameter n as a number becomes cumbersome. And I want you to understand this. So let's write out a couple of these explicitly. So the Taylor polynomial of order 0, okay? So t sub 0 of f comma x star at x is the sum where k varies from 0 to 0. That means that I only have k equals 0 here. K, a zero derivative of a function is just the function itself. 0 factorial is 1. This to the power 0 is 1 as well. So this is nothing but f of x star. Now this is a constant polynomial. The variable is x, okay? I fixed x star. This is a constant polynomial. What is t sub 1? Taylor polynomial of order 1. So now I need to add k from 0 to 1. So I need to have the previous term plus when k is equal to 1, f to the 1 in paren means f prime, first derivative, divided by 1 factorial. 1 factorial is 1, so this is nothing but f prime of x star, and this is going to be x minus x star to the raised to the power 1. So this is minus. Okay. Now, to make this similar to our notation from before, because we have seen this before, instead of using x, let me change the variable, because the way I'm imagining this is that at the very least, this should be an approximation for f when x is near x star. So if I were to make the change of variables, x minus x star equals h, so that x is x star plus h, then what happens here? This means that t1 of f comma x star at x, but x is nothing but x star plus h, is, well, this is the constant term, just this, and then x minus x star is equal to h. Okay? And of course, we've seen this expression before. This was the equation for the unique line that is tangent to f at x star. Right? So this is, let me write it in a different color. Okay, let's do one more. Taylor polynomial of order 2. So it's T sub 2. Oh, I'm going to write it in blue. So the 0th order term is going to be the same thing as the 0th Taylor polynomial. So you see these Taylor polynomials are nested in a sense. To get the next Taylor polynomial, all you need to do is to add the next term. So I can start with this and then add the 2nd order term. That's my 0th order term plus 1st order term plus 2nd order term. But you see, when k is equal to 2, I need to correct the 2nd derivative by 2 factorial. 2 factorial, of course, is nothing but 2. And then I need to multiply it by x minus x star raised to the power 2. Okay? Now this is new, you see. But in a sense, it's the same sort of idea. The expectation, your expectation at this point should be that this, in a sense, is the unique parabola, right, 2nd order polynomial, that is tangent to f. It turns out that that is not quite correct if you just look at tangent in the sense of order 1, because remember, in the definition of tangency, we wanted the difference of the functions to be O of h, but if I were to look at O of h squared, then this would be, hopefully, the unique quadratic polynomial that is tangent. Okay? Let me write this also in these variables also. So this, in the other variables, becomes like this. Times h plus f double prime x star divided by 2 times h squared. Any questions about this? So far we didn't have access to the 2nd order term. We looked at the 1st Taylor polynomial, and we sort of like said, plus higher order terms gives me my function f. But if you have 2 derivatives, or 3 derivatives, whatever, it is reasonable to expect that you should be able to expand it even further and look at even smaller terms, right? For h small, h squared is very small compared to h. So this is negligible. The effect of this is negligible compared to the effect of this. But still, it's there. Okay, I want to do one more thing. Let's first look at this, for instance, the 2nd Taylor polynomial. The 2nd Taylor polynomial at x star is equal to f of x star. So if I plug in x equals x star, this is constant. This becomes 0, so this vanishes. This becomes 0, so this vanishes also. How about the first derivative of the Taylor polynomial? I'm fixing x star, okay, and the variable is x. So I'm looking at d of this by dx. Let's compute this. So d by dx of t sub 2 of f comma x star at x is what? This is constant, it vanishes. This is constant, and then I need to differentiate this with respect to x. So this is just going to turn into f prime of x star plus this is constant. Then I need to differentiate this. This is going to give me 2 times this polynomial. Which means that the first derivative of the second Taylor polynomial at x star again is going to be the same thing as the first derivative of f itself, because this guy is going to vanish. So t sub 2 of f comma x star prime, that's an abbreviation for this, evaluated at x star is the same thing as f prime of x star. And of course, if I were to differentiate the second Taylor polynomial 2 times and then evaluate, I would get back the second derivative of f at x star also. Okay. So somehow, you see, this is also telling you why you need to have these correction factors. You're putting these correction factors so that whatever polynomial this is, at least at x star, its derivatives match up with the derivatives of the function that you started with. That's what you're trying to do. 0th derivatives match, first derivatives match, second derivatives match, and if I had higher order derivatives, they would have matched also. Okay, any questions about this? I am going through these calculations because when you write the Taylor approximation theorem with these ends and stuff like that, it becomes very hard to sort of follow what is actually happening. You already know the content of it, at least for n equals 1 or 2, whatever, is the point. Any questions? Okay, so here's the Taylor approximation theorem. I think if I teach this class again, I'm going to cover this way before than the last week of classes. But the point is that like one part of it is going to involve some integrals. And so you can't really cover this before covering integration. So maybe we could have sort of postponed infinite series business. And discuss it after Taylor approximation. But anyway. Okay. Taylor approximation theorem. Fix an n, non-negative integer, and let's let f to be Cn. N times differentiable with the nth derivative continuous. You actually don't need the nth derivative to be continuous, but Cn is a natural space, so. And let me let x star to be a point in I. Then the nth order Taylor polynomial of f at x star is the unique degree n polynomial that is tangent to f of order n. That is to say, at most n, of course, because maybe the nth derivative vanishes, in which case you wouldn't call this a degree n polynomial, is a unique degree at most n polynomial such that f of x star plus h equals t sub n of f comma x star at x star plus h plus little o of h raised to the power n. As h goes to 0. For n equals 1, you have analyzed this statement in a previous problem set, and it was in the second midterm as well. All the ins and outs. Okay. 2. Now, if you have slightly more properties, that is to say, if it turns out that f is not Cn, but Cn plus 1, then in fact, you can say something about the remainder. So the difference between these two guys. So if you have more regularity, then you can say more. And for any h non-zero, okay, maybe let me state it like this. For any x that is not the same thing as x star, there is, let's say, a point x dagger that is strictly between x and x star. Such that f of x equals t sub n of f comma x star at x plus, now it's going to look pretty much the same way as the n plus first term, except that you're evaluating the derivative at this point instead of x star. So if it were the case that x dagger equals x star, this will be literally the n plus first Taylor polynomial. But you see, this base point is the wrong point. It's a different point. And again, if f is in Cn plus 1, there's also an integral form of this remainder. Let's see. Yes. For any x that is distinct from x star, f of x equals the nth Taylor polynomial plus 1 over n plus 1 times the integral from x star to x of x minus y raised to the power n, I think. Let me see. Yes. Raised to the power n multiplied by the n plus first derivative of f at y dy. So what people do is they call the difference between the so maybe I should, for consistency, I should rewrite this using this other notation as well. So in the other notation, this becomes like this. So f of x equals Taylor polynomial at x plus little o of x minus x star in absolute value raised to the power n as x goes to x star. So what people do is they call the discrepancy between these two, the function itself and its nth Taylor polynomial, the nth remainder. Okay? And if you want, all of these statements are about the nature of this nth remainder. So this is your error term that you're trying to sort of make as small as possible or understand. So R sub n of f comma x star is f minus the nth Taylor polynomial. So the first statement says that the remainder is small. Second statement says that I can actuate the remainder to be of this form for some x dagger. Third, it says that I can actuate this remainder as a certain integral. For different applications, these sort of like forms turn out to be more important, more convenient. Any questions about this? Now, this is a lot to digest, so let's try to parse this. If I were to, let's say, fix n equals 0, so I have a continuous function. When you encounter statements like this, what you want to do is you want to sort of fix the variables so that the statement becomes easier to understand. So I have a continuous function. Okay, C0 is continuous. Zeroth polynomial is nothing but f of x star. So what does this first one say? Well, what I can do is the following, right? So f of x is the same thing as f of x star plus f of x minus f of x star. I can write it like this. And I know that if f is continuous, certainly as x approaches x star, this has to decay. Okay? So this is going to be to the order 0. Order 0 means little o of 1. It just means that it goes to 0. So this is little o of 1. So that's the content of the first item. Okay? Any questions about this? So for n equals 0, Taylor approximation says basically something that is equivalent to the definition of f being continuous. It says that for x near x star, f of x is near f of x star. That's what it says. That's the definition of continuity. So what about the second item? The second item says that if n is 0, that means that f is continuously differentiable. So second item, and also the third as well, f is continuously differentiable. Okay. So again, this is f of x. This is, again, n equals 0, which means that this is f of x star. So this just says f of x equals f of x star, first derivative, blah, blah, blah. So let me just write it. That's what this says. Item 2 says this. But certainly this has to be true. This is the content of the mean value theorem. It says that between any 2 points that are distinct, there is some point such that the rise over run, right? So this the difference is this, the rise. And if I were to divide it by this, I would get the derivative. This is mean value theorem. And third, again, n equals 0. Well, if f is differentiable with the first derivative continuous, I have this expansion. So f of x is the same thing as this, based on pure algebra. But then, by the first fundamental theorem, I know that this is the integral of f prime. So in a sense, item 1 in Taylor approximation is pretty much the definition. Item 2 is mean value theorem. Item 3 is fundamental theorem of calculus. But for higher derivatives. Okay? Any questions about this? I guess we're going to have to spend Friday's class proving at least items of this thing. But you see, it looks scary, I know, but it's something that you're familiar with. Trust me. Okay? Any questions? Okay, thank you. I'll see you on Friday. Okay, let's start. Good morning. So this is our final class where we're going to discuss new topics. So on Wednesday I had described this Taylor approximation theorem. I had stated it, and I told you what happens when n equals 0. We said that when n equals 0, item 1 really tells you something equivalent to continuity. Doesn't really say anything much. Item 2 says something basically that is equivalent to the mean value theorem. And item 3 says something equivalent to the first fundamental theorem of calculus. The point of Taylor approximation is that it somehow incorporates all of these ideas so that you get to use higher order derivatives also. Okay. And let me mention that the proof of it is not really very sophisticated, actually. We're just going to use tools that we're comfortable with, we have been comfortable with throughout the semester. It's just that because you have many derivatives and stuff, there's a lot of bookkeeping involved relative to the other sort of proofs that we've done before. Okay, before I get into the proof of this, I should mention, so we have our final next Friday. I just sent an email like half an hour ago about that. So it's going to be slightly longer than usual because it's a 2-hour exam. The final problem set is up also. That's going to be due next Friday, midnight. It's going to be about Taylor approximation and stuff like that. What else? I don't think I have anything else to say about sort of logistics and stuff. So maybe I should ask you, are there any questions about anything? Okay, so let me remind you what this Taylor polynomial of degree n was. So the first statement says that if f is n times continuously differentiable, then its order n Taylor polynomial at x star is in fact the unique polynomial of degree at most n, that is tangent to f at x star to order n. So I'm gonna remind you what this means. So let me first remind you what this Taylor polynomial was. So this Taylor polynomial is a function of x. You see, I have fixed x star. And so this should be the partial sum of the power series up to the nth term. 0 to n. Kth derivative of f evaluated at x star divided by k factorial times x minus x star raised to the power k. This was my Taylor polynomial. Now, it is also useful to think of it. So this takes an input x here. So in the proof, we're going to have to think of this Taylor polynomial to be a function of x, but eventually we're going to start shifting the base point where we're sort of looking at this approximation also. So this was this. Okay, let me also set up this notation. R sub n, it's going to be the remainder. So it's the difference between the function f, the original function, that is quite possibly not a polynomial function, maybe something like exponential or something, and the difference between that and the nth Taylor polynomial. This is the remainder. Okay. Now, what do I mean by this symbol? This is shorthand for saying that f of x, let's say, is equal to this plus terms that decay faster than the distance raised to the power n. So let me write it here. Okay. Maybe I can just start the proof and write it there. So this means that f of x equals the Taylor polynomial plus little o of x minus x star, this distance between the base point and the point at which you're comparing these two functions, raised to the power n. And little o as x approaches x star. This is what this means. Okay. Now, in a previous problem set, you verified this, in fact, for n equals 1. For n equals 1, you just get the linear approximation. The point of Taylor approximation is that you get to have higher order terms. Now, I'm going to leave to you to verify that this Taylor polynomial is a unique polynomial that does this. The proof of it is pretty much the same way as you did in the problem set before for n equals 1. It's an analogous proof. Perhaps one thing you can say is that if I had two polynomials of degree at most n that are tangent at a point of order n, then it must be the case that all of their coefficients must be equal. Because otherwise, I would have lower order terms, and lower order terms does not decay faster than higher order terms. They decay slower, which means that their coefficients must be 0. So they cannot be there. So that's how we prove this uniqueness. But of course, we need to show existence also. Now, we had mentioned this on Wednesday. We have these correction factors here. So we have 1 factorial, 2 factorial, and so on. And we mentioned how these numbers are there so that the derivatives of this Taylor polynomial at x star match with the corresponding derivatives of the original function f. So we have, if this is not clear to you, this is also an exercise. It's a very nice exercise as well. So for any k, the kth derivative of the original function evaluated at x star is equal to the kth derivative of its tangent of its Taylor polynomial of order k at x star also. This was my polynomial. I differentiated it k times, and then I evaluated at x star. Okay? Now, if this is the case, then it is also true that for any k, the derivative, the kth derivative of the nth remainder is 0, because this remainder is the difference between these two functions after all. Okay. So what I can do is the following. So the first statement, you see, is about this tangency, this order n tangency. And instead of looking at this equation, of course, I can send this Taylor polynomial to the other side. This really says that this remainder function is O of distance raised to the power n. So if I can control the absolute value of this remainder, then I would be done. So let me write it here. Well, I can subtract from this its value at x star, because I know that for k equals 0, this is just the function itself. I know that the remainder at x star is equal to 0. This is 0. And of course, this statement really is for x not equal to x star. I know that when x is equal to x star, these are equal on the nose. So I need to choose x to be distinct from x star. Well, if that is the case, then by the mean value theorem applied to this function, I know that there is some point strictly between these two guys such that I can rewrite this. in terms of its first derivatives. So, like this. Remainder function differentiated once, evaluated at some point x sub 1, an absolute value, times the distance between these two inputs. Let's say x were here and x star is here. I'm saying for some x sub 1, by the mean value theorem, I get to do this. But then I can keep iterating this idea. Let me do one more. After all, the first derivative of this remainder to itself is differentiable, which means that I can apply the mean value theorem to this guy in and of itself. Because I know that the first derivative of this function evaluated at x star 2 is 0. So I can just subtract from this expression. Differentiated, evaluated at x star in absolute value, times, I shouldn't forget this part. So the first derivative of this remainder itself is a differentiable function, and I'm looking at its values at this point and this point. Again, by the mean value theorem, there's some other point strictly between these two, such that I can again peel off one more derivative. Second derivative now, evaluated at x2, that is strictly between x and x sub 1. Oh, it should be the other way around probably. I'm going to do this like this, times the distance between x sub 1 and x sub star. X minus x star, like this. So I applied the mean value theorem twice. First, I applied it to the remainder function between these 2 points. That gave me this point. Then I applied the mean value theorem between these 2 points to the first derivative. That gave me this point. But I can keep iterating this idea. Eventually, I'm going to be done with all of these derivatives. But the last derivative, is going to be where I stop. So let me delete this as well. Let me just write it like this. Ultimately, you're going to be left with the remainder function differentiated n minus 1 times, evaluated at some x sub n minus 1. It's this point, let's say. In absolute value. But then let me fast forward this a little bit. This is of course also equal to this, because I know that the n minus first derivative of the remainder at x star 2 vanishes. So again, I can subtract a 0 here, like this. Then let me divide this by their distance, so that now I have here these terms, x sub n minus 1 minus x star in absolute value times dot 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 all the way up to x sub x star. Okay. Now note that each of these previous factors are bounded by this, because each of these terms are between the previous one and x star. Which means that this is bounded by x minus x star raised to the power n. And I know that if I take x to 0, or rather x to x star, x sub n minus 1, 2 has to converge to x star. And I know that the remainder is n times differentiable with the nth derivative equal to 0, which means that this ratio 2 goes to 0. Okay, so I was able to bound the remainder by the distance of x and x star raised to the power n times some constant that goes to 0. That's little of this that I wanted. Okay, so let me show this. Now you see it gets somewhat complicated to keep track of the number of derivatives and stuff like that, because so far we were just thinking of the number of differentiability as sort of like an assumption. But ultimately, the number of differentiability too is just a number. So to really understand this, I would highly recommend going through the proof by yourself for n equals 2, for instance, okay, so that you have the second order approximation. Okay, any questions about this? So the punchline is, for the first part, tangency of order n of the Taylor polynomial, you just apply mean value theorem n times. Okay, or maybe n minus 1 times, finitely many times. Okay, so that's the first part. For second part, we need to cook up a point, x dagger, that is strictly between an x and x star, such that the remainder is of a certain form. Let me remind you, this was the claim for the second part. If x is not equal to x star, there is an x dagger strictly between x and x star. Such that the remainder has the explicit form like this. n plus 1 factorial times x minus x star raised to the power n plus 1. So it's almost like the next term in the Taylor polynomial, except that you're evaluating the derivative, the appropriate derivative at the wrong point. So how can I try to come up with this x star? Any guesses? Any strategies that I can try using? There was one sort of like thing that I suggested that you always think about whenever you're given 2 points and when you're trying to find a point that is strictly between them. There's pretty much only one sort of method. Okay, mean value theorem. So we need to, more specifically, I'm going to use the Rolle theorem, which is like a specific case of it. But the point, of course, is that to which function can I apply the mean value theorem so that a critical point of it detects this one. Now this perhaps is not very clear, but if you play around with it a little bit, you find this function. I'm going to define a function phi. And this is where things get complicated, okay? By phi of y is going to be, let's see if I mess this up. So I fix x and x star. Those two are fixed, okay? Now I'm defining this to be remainder function at y, my input, evaluated at x, minus remainder function at x star, evaluated at x again times x minus y divided by x minus x star raised to the power n plus 1. Okay. Now, of course, x and x star 2 are variables here, and if you want, you can think of the partial derivatives of this expression, but this is, since this is like a single variable class, we're just pretending that we don't know these things. Let me just double check that I wrote the correct thing. Yes. Now I'm going to leave it to you to verify that phi of x and phi of x star are 0. And any critical point of phi precisely satisfies this equation. And so d phi by dy at y equals 0 if and only if this happens. In fact, okay. Let me just give you the derivative. You can verify that this derivative is indeed correct. It's a calculation, okay? It takes a while. Okay. And d phi by dy at y is equal to x minus y raised to the power n times minus the n plus first derivative of f evaluated at y divided by n factorial plus n plus 1 times the remainder function at x star evaluated at x divided by x minus x star raised to the power n plus 1. It's a calculation, okay? You just keep track of everything, and this turns out to be true. I did it before. It just takes a while. So I'm going to leave it to you to verify this. But the point is that I have a differentiable function phi that is 0 at 2 points. Let me just remind you. So this phi is some function such that it is 0 here, it is 0 there. Rolle tells me that eventually, okay, this is like a bad thing, but eventually, somewhere in between, the derivative is going to be 0. So by Rolle theorem, or by Rolle Lemma, I know that there is some x dagger such that the derivative of phi at x dagger is 0. But x dagger is strictly between x and x star, which means that in order for this product to be 0, this cannot be 0, which means that the other part has to be 0. And if you sort of like rewrite everything, you realize that this happens only if this happens. Okay. That's the end of the second part. Any questions about this? So mean value theorem again. You keep applying mean value theorem or Rolle Lemma, whatever. We had discussed these critical points, critical values, all that stuff. And we said how, well, I guess critical values are pretty much 0. But critical points, we said that critical points are important. So you differentiate something, set it equal to 0. That tells you something important. The art of it, of course, is to figure out to which function you should be applying so that you get your result. Okay. And in fact, there's also a Cauchy mean value theorem version of this, where instead of this function, you have some more complicated function. It's the same idea. Instead of using the mean value theorem, you use the Cauchy mean value theorem, gives you some other estimate. Of course, why would you want something like this? Well, this is the remainder. This is your error term, if you want. You're trying to approximate f using a polynomial, and this is your error. If you can So the benefit of this formula is that once you have this point, if you know that the n plus first derivative of your function is bounded, that gives you an upper bound. Okay? So not only is this guy little o of distance raised to the power n, but in fact, if the n plus first derivative is bounded, it's in fact big O of distance raised to the power n plus 1. It's slightly better of an approximation. Okay? Some people are interested in these kind of things. Okay, and the third part, in fact, we're going to use induction. Okay? Let's remember that as well. Induction is going to be, maybe I should ask you, how can I use induction to prove item 3? So this is like an integral formula. If I were to send this to the other side, this says that the nth remainder can be written as this integral. How can I induct?
I guess, yeah. No, this isn't inductive, but you could say something about like the remainder of it, and then say that the remainder has to be that integral.
But what is so I'm saying I want to use induction. What should be my index for the induction?
Probably n.
Right, so this is kind of weird, but this is how you use induction in more sort of applicable situations. Induction will be on the number of differentiability. Okay? And this is like a review. Remember, we had discussed induction maybe in week 1 or 2. See how we end up using it. We'll use induction on n. So for n equals 0, that's my base case, remember. What does it say? It says that if f is continuous, then for any input value x, this happens. Well, I know that f of x can be written as f of x star plus f of x minus, of course, if n is 0, that means that f is continuously differentiable. Okay. I can just write it like this, but then I can use the fundamental theorem of calculus, the first part, to say that this indeed is nothing but the derivative of the integral of f. Integral of the derivative of f. From x star to x we had discussed how this value of the function at x star is nothing but the 0th order Taylor polynomial. 1 over 0 factorial is just 1. If n is 0, n plus first derivative is just the first derivative. And this is raised to the power 0. So this covers the base case. Now suppose that the formula works for n. I want to show that it also works for n plus 1. So now I need to assume that f is, let's say, Cn plus 2. Because if n is n plus 1, then n plus 1 is n plus 2. Induction. So what was it? Induction step? Whatever. Induction case. Induction step. say this, and that the formula works for one less degree. Now, what do I want? So let me see. So let me start with the integral. Then we're going to relate it to the remainder. So for f in Cn plus 2, I should be seeing an integral of the following form. X minus y raised to the power n plus 1 times the n plus second derivative of f evaluated at y dy. Yes. So somehow I want to relate this to the same expression, but exponents one less. And ultimately for this, I can use, there's pretty much one thing, which is integration by parts. Okay. So what I'm trying to do is, I'm trying to lower the number of derivatives for f, which means, and this I can differentiate more if I want it, you see. So somehow I want to transport one of the derivatives here to here. I think that's what I want. Let me see. This is a finicky proof. And I don't want to waste your time as I'm trying to figure out the correct thing. Oh, I see. I started from the other way around, actually, to apply the integration by parts. So let's do it the other way around. So this is the integration formula that I have for n plus 1. Right. So I'm going to call this guy u, and the remainder dv in integration by parts. So let's do that. So let me write it here. So my u is going to be the n plus first derivative of y, and dv is going to be the remainder, x minus y raised to the power n times dy. And so what is du? Du is the n plus second derivative of f dy. And v is supposed to be x minus y raised to the power n plus 1 divided by n plus 1, but with a factor of minus because I'm integrating with respect to y. So these are my by parts formulas. Okay, so this is of the form u dv. Okay, let me remind you the integration by parts. It says that u dv, the integral of this, is uv minus v du. And so writing this out gives us the following. U times v is this. N plus first derivative of f evaluated at y times this divided by minus n plus 1, where y is evaluated at x star and x, minus v du. But I have another minus here, which means that I can just use a plus here. And then this is a constant, I can take it out. 1 divided by n plus 1 integral from x star to x v du. Okay. Now you see this is nice because if I plug in y equals x, this is 0, so this part is going to vanish, which means that I'm only going to have one term coming from this. Let me continue from here. You see, even in single variable calculus, you end up doing sort of multivariable ultimately. And that is why perhaps one of the perhaps soft prerequisites for this class is also multivariable calculus. So I'm going to continue from here. Now this is equal, so if I plug in y equals x, that vanishes, minus minuses, which means that this minus is going to cancel out, and I'm going to be left with this. n plus 1 times this raised to the power n plus 1 plus this term. Let me just write it I sub n plus 1. The integral with n plus 1 as the index. And so if I denote that by I sub n plus 1, this integral is I sub n really. Let me use blue. Which means that I have this formula. Okay, so we didn't use anything about the induction step so far. So now I can say the following. N plus first remainder right, okay. This is f. Maybe I should plug in x as well. At x is f of x minus the n plus first Taylor polynomial at x. But this is nothing but the nth Taylor polynomial plus the next term. So let me be explicit. K from 0 to n plus 1, kth derivative at x star divided by k factorial times x minus x star raised to the power k. So this sum I can take all the way up to n, and then I would have an extra term. That would give me this minus n plus first derivative divided by n plus 1 factorial times x minus x star raised to the power n plus 1. And now I can use the induction, and I can say by induction, I can say that this remainder equals this. Oh, but you see, isn't this nice? This part cancels out with this, which means that if I were to substitute instead of I sub n, this expression, this sum would end up being the integral with index n plus 1. By the principle of mathematical induction, then, the statement is verified. Questions? comments? Okay, we have about 5 minutes. Initially, I was thinking of discussing this operator calculus, but I think I'd rather not discuss new material. It's a nice thing, of course, but maybe in the last 5 minutes we can sort of go back to the syllabus and see what we did and how far we've come. So let me just read out again the course description. This is a proof-based class, and the emphasis will be on developing mathematical maturity. I think pretty much all of you develop some mathematical maturity. You see, mathematical maturity is not really being able to do math, but more about not being fazed by not understanding something. And throughout the semester, I think you did pretty well. I've bombarded you with crazy questions, crazy problems, and you've sort of worked on them, and you've sort of experienced the pain of doing math, in a sense. So in the future, you may not be doing math, but ultimately, probably there's going to be mathematicians around you if you're doing something related to science. In your group, there could be mathematicians. And at the very least, now you know, you have some idea as to the type of training they go through. And of course, if you end up going to grad school for math and stuff like that, there's going to be more of this. It just gets harder and harder as time goes by, as you've experienced in this class. Like, the next problem set is always harder, in a sense, except in certain situations. In particular, on rigorous argumentation, rather than calculation of the values of certain limits, integrals, or derivatives. So we learned how to construct proofs, parse proofs, understand proofs, all that. But at the same time, I hope I gave sufficient emphasis that pure math, or mathematics, is not only about rigor. It's also about sort of like having intuition and developing your intuition. And then you try to prove something, and then it doesn't work. And then you sort of adjust your intuition, and that sort of like guides how you should be proving things. So it's a reciprocal thing, in a sense. We'll start with elementary logic and set theory, right? So we discussed all these like logical symbols and so on. We discussed main methods of documentation that are up to the modern standards of mathematical rigor. And again, we've seen how this notion of proof changes over time. And we said, like fundamental theorem of calculus was proved even before the notion of proof, as we understand, was established, right? But they still had an idea as to what the argument should be. And then discuss differential and integral calculus of single variable real valued functions. As adjacent topics, we'll study the convergence and divergence of sequences and series of numbers and functions, which we did. There's a bunch of other things that I wrote here. Maybe I should mention, in the tentative schedule, I think you are pretty close. We skipped a couple of items. Most specifically, I haven't emphasized this Cauchy stuff that much, but still we discussed it maybe last week a little bit. One thing I skipped was the Cauchy principal value stuff. It's something about improper integrals. It gives you sort of like one way of associating numbers to integrals that possibly diverge. We didn't discuss in detail this Riemann rearrangement theorem. And also related to this was this idea of multiplying power series, or infinite series more generally. We also didn't discuss those. And likewise, it's not going to be in the final. And apart from that, we didn't discuss elementary functions, exponentials, logs, and stuff like that. And so those three were the main three things that I skipped. But instead of that, we did many other things. And I think we covered plenty of topics. I hope you feel like you got your money's worth. I certainly did my best giving you a good class. But thank you. That's it.